We are converting the chapter 4 into the form of question answer, and this is very useful to the student of SEE examination. And beside this chapter is very useful to the science student of the school. Okay, this is part 4. Let's start. Question number 37. Why weight of a body is more at pole than the equator? Now we can answer this way. Weight of a body is the product of the mass and small g, that is W equal to mg. Mass of the body is constant, but small g is inversely proportional to the square of the radius of the earth. And Earth's radius is less at pole than the equator, so small g is more at pole, and the product of mass and g, that is weight, is also more at pole than the equator. Look at this. This is the real answer. We have to write this much only in the examination. But for better understanding, I want to say something more with the help of diagram. Look at this is, let's say, Earth, and this is North Pole and this is South Pole. And these 2 points, if we join them, then we can say this is equatorial region, the bulged part of the Earth. The polar radius of the Earth is short, but equatorial radius is long. We know that g is inversely proportional to the square of the radius of the Earth. Since radius of Earth at North Pole is less, so value of g is more, and it is found 9.832 meter per second square at North Pole. Since the radius is more at equator, that's why value of g is less. It is found g equal to 9.798 meter per second square. We can go through a mathematical calculation also to understand it very clearly. Look at this, W equal to mg. If we take 10 kg mass at North Pole, then its weight will be 10 kg multiplied by g at North Pole, and its value will be 98.32 Newton at North Pole. And the same formula we are using for the same body when taken to equator. Let's say at equator, the same 10 kg is when multiplied by the g of equator, then we'll get 97.98 Newton. Look at these two values. At pole, the same is weighing 98.32 Newton, but at equator, the same is weighing 97.98 Newton. Less at equator, more at pole. We can understand this way very nicely, but we don't have to show this with diagram and mathematical expression. We have to write the answer which is written on the screen in white letter. Okay, let's go to another question. Weight of a body is less at the top of the mountain than the bottom. Why? Now I want to show this with diagram. Let's say this is Earth and this is a mountain on the surface of the Earth, and we know that radius of the Earth is more at the top of the mountain than that of the bottom, and g is inversely proportional to the square of the radius of the Earth, and radius is more at the top of the mountain, that's why g is less. And if g is less, we know W equal to mg, mass remains same but g is less. It means the product of g and mass, that is weight, also becomes less at the top of the mountain. But on the other side, look at this, more g at bottom of the mountain, and weight is more. Why? W equal to mg and mass is same, g is more, and the product of more g and mass of the body, that is the weight of the body, is more at the bottom of the mountain. Now we can answer this way. We don't have to show all these, but this is for better understanding. We can write this much only. Weight of a body is the product of its mass and small g. Mass of the body is constant, but g is inversely proportional to the square of the radius of the Earth. Earth's radius is more at the top of the mountain than the bottom, so g is less at the top, and the product of g and mass, that is the weight of the body, will also be less at the top of the mountain. Let's go to another question. Weight of different substances at a place is same, but weight of the same substance at different places is different. This statement is correct or not? Now looking at the statement, weight of different substances at a place is same, this is wrong. We can understand easily. If we have two stones, one is big, another is small, at a place their weight will be certainly different. And so different substances wouldn't have same weight at a place. But weight of the same substance at different places is different, the second part of the statement. Yes, it is true. Just before this question, I told you that a 10 kg mass weighs more at pole, but the same 10 kg mass weighs less at equator. Okay, we can write this way. The first part of the statement is wrong, but the second part is correct. Weight of a body depends upon mass because it is the product of mass and g. Mass of different substance is different, so the product of mass and g, that is weight, will be different at the same place. But second part, value of g is different in different parts of the earth, so the product of g and mass, that is weight of the same body, will be different in different parts of the earth. Okay, let's go to another question. What is free fall? Now, what is free fall? It's very easy to write. A body is said to be in free fall if it is falling with the acceleration due to gravity without any resistance. It is possible only in vacuum. If a body falls in air, it will face certain resistance, and free fall is not possible in air. It is possible only in vacuum. Okay, let's go to another question. What is weightlessness? A body becomes weightless during free fall due to the lack of reaction force. Such a condition is called free fall. Okay, let's go to another question. Why do we feel uncomfortable in a giant wheel when it is moving downwards? What is the reason? It's very simple to answer. When a body accelerates downward, it loses its weight and becomes weightless due to free fall. So, when a giant wheel moves downward, we lose our weight and we feel uncomfortable. Let's go to another question. Write down differences between capital G and small g. And for this, we have to make a table, and capital G and small g. First, we'll write the meaning of this symbol. It is symbol of gravitational constant and it is symbol of acceleration due to gravity, that is small g. Okay, number 2, we can define them. Gravitational force between two unit masses separated by a unit distance is called capital G, means gravitational constant. It was defined in previous class also. And secondly, an acceleration developed on a freely falling body due to gravity of the earth is called small g, that is acceleration due to gravity. It was also defined in previous class. Okay, let's go to third difference. Its value. Its value is 6.67 into 10 to the power minus 11 Newton meter square by kg square. But the value of g is, small g is, its standard value 9.8 meter per second square. Why we are saying standard value? Because it varies from place to place of the earth and standard value is taken as 9.8 meter per second square. Now next is capital G is a scalar quantity. It has no any definite direction. It is not unidirectional quantity. That's why it has no direction. It has value only, and if a physical quantity doesn't have direction, then it is scalar quantity. Now next, it is a vector quantity. It has both the magnitude and direction. Its magnitude is 9.8 meter per second square and it has direction, that is towards the center of the earth. So this is a vector quantity. Okay, its value remains constant throughout the universe, but its value varies from place to place of the earth. Okay, let's go to another question. Write down differences between mass and weight. Now we have to make a table, and mass in left hand side, weight in right hand side. Now first difference is definition. Quantity of matter contained in the body is called mass of the body. Okay, what is weight? The force with which earth attracts a body towards its center is called weight of that body. Okay, let's go to second. It is measured by using physical balance, beam balance. Now, it is measured by using spring balance. Third, it is a scalar quantity. It has only magnitude. It has not a definite direction. Quantity of matter doesn't have any definite direction, but it is a vector quantity because it has not only magnitude, its direction is towards the center of the earth. Now, its value remains same at any place of the earth. If we take certain mass, a piece of stone or something, to different parts of the earth, quantity of matter remains same. But this weight varies from place to place of the earth. The same body weighs more at certain place, same body will weigh less at another place. Okay, another difference. Its SI unit is kilogram. There are other units also, but SI unit is kilogram. But its SI unit is Newton. Now we have to go to another question. Mass of a body cannot be measured in the space. Why? This is very interesting. We cannot measure mass in the space. Now let's take example. I want to show it with the help of a balance. Look at this is a beam balance. We have here a beam. If we want to measure the weight of this toy car, then we have to put tender mass at another pan. And actually what we are doing, we are comparing the gravity acting on this toy car with the gravity acting on this standard mass. When beam becomes balanced, then we say that this toy car weighs 500 gram if this standard mass is of 500 gram. It means mass is measured with the help of gravity force. We cannot measure mass without the help of gravity force. So, in space, there is no gravity force at all. And that's why we can answer this way. We don't have to show all this diagram. This is just for understanding. Mass of a body is measured by using beam balance. And it is measured by comparing gravitational force on the earth, we can say gravity acting on an unknown mass with the gravitational force acting on a standard mass. In the space, there is no gravitational force, so mass of the body cannot be measured in this space. Okay, this is our answer. Now let's go to another. How can you prove that a feather and a stone have same acceleration during free fall? They have same acceleration is told in the question, but how can we prove? It means we have to explain an experiment. Look at this diagram. A 1 meter long tube is taken, which is previously filled with air, and a feather and a small piece of stone is taken into it, and once we suddenly invert it, then what can we see? The stone falls faster, but the feather falls slower. The stone strikes another end first, and then feather comes down later. This is because of the air resistance. Air resistance can oppose the motion of this feather because feather has very less mass, and gravity acting on the feather is very less. It can be neutralized by the air, and so it won't fall with acceleration due to gravity. But the stone, its mass is comparatively very high, so gravity acting on the stone cannot be neutralized by the air resistance, so it falls with acceleration due to gravity. That's why stone comes first and later feather falls down. But when the air from the same tube is taken out and the tube is now vacuum in second case, and if we quickly invert the tube, then what is seen? Both of them falls together up to the another end. It proves that whether the body is light or heavy, whether the mass is less or more, they have same acceleration in vacuum. Okay, we can write this way. To prove this, both of these should be placed in a 1 meter long glass tube. When the tube is quickly inverted, stone falls earlier than the feather. If air is pulled out with the help of vacuum pump and again the tube is inverted, then the stone and feather falls together in the tube. Both of them fall with the same acceleration due to gravity because there is no air and both have free fall. Thus, it is proved that during free fall, stone and feather falls together. Okay, let's go to another question. The value of acceleration due to gravity on the moon is 1.67 meter per second square. What does it mean? We have to write the meaning of this value. It means when a body is dropped from certain height on the moon, then its velocity increases by 1.67 meter per second after every 1 second. At the end of first second, its velocity will be 1.67 meter per second. At the end of second second, again 1.67 meter per second velocity will be added and it will fall faster. At another 1 second, I mean to say at the end of third second, again 1.67 meter per second velocity will be added to the previous velocity. This way, in every second, its velocity will increase by 1.67 meter per second. That's why it will fall with the acceleration of 1.67 meter per second square. Let's go to another question. Astronaut feels weightlessness in a space aircraft. Why? Gravitational force between Earth and space aircraft is mutual force. They neutralize each other. So, the weight of the astronaut is the force of attraction of the space aircraft acting on his body. Since the mass of the space aircraft is very less, so its gravitational force, that is weight of the astronaut, will be negligible and he feels weightlessness. Okay, let's go to another question. A stone and a piece of paper are dropped simultaneously from same height on the lunar surface. Which one will fall faster? We can answer this way. Both the stone and paper fall simultaneously. We have to remember that there is no air on the moon. Moon doesn't have atmosphere. So there is no air resistance and acceleration due to gravity is same for every substance irrespective of their mass. Hence they fall together. Now let's go to another question. The value of universal gravitational constant is 6.67 into 10 to the power minus 11 Newton meter square by kg square. What does it mean? We can write this way, very simple. It means two 1 kg masses separated by a distance of 1 meter attract each other with a force 6.67 into 10 to the power minus 11 Newton. Okay, now let's go to another. The weight of a body is less on the moon's surface than on the Earth's surface. Why? We can write its answer like this. According to Newton's law of gravitation, the gravitational force, actually gravitational force is also weight, between two bodies is directly proportional to the product of their masses. The product of the mass of the moon and the body is less than the product of the mass of the earth and the body. Hence, weight of the body will be less on the moon than on the earth. To understand the same answer very nicely, I want to show it with diagram. Let's say this is earth and this moon. And a body is lying on the earth and the same is taken on the moon. And what is the answer? The weight of the body will be more when it is on the earth, but weight of the same will be less when it is on the moon. Now, how we answered this? Actually, the weight of the body on the earth is the gravitational force between the earth and the body. In the same way, weight of the body on the moon is the gravitational force between moon and the body. And since mass of earth is very huge, that's why gravitational force is huge on the surface of the earth in comparison with the moon, because according to Newton's law of gravitation, gravitational force between two bodies is the product of their masses. Earth's mass is more, and that's why product of these two masses will be more, that is weight will be more, but the mass of moon is less and the product of the mass of moon and the body will be less. That's why the weight of the same body will be less on the moon. Okay, this much for today.